Okay. I hope recording is started.
Yeah, I did.
Well, hello to everyone. Today we have first webinar, as it turned out, on this course. My name is Alex. You already know me, and you're welcome. So you're already familiar with the image classification, object detection, object segmentation. You already know what is deep RAD. You know what types of object trackers there are. You know the idea behind sort. You know the idea behind deep sort. And some of you maybe already have started the final project or will start soon. So today we will meet a few more well-known trackers and figure out how to evaluate the quality of the tracking. Then I will show you the architecture of the average surveillance system. This may help you in completing the final project and also in your professional life. And at the end of the webinar, we will have time for question and answering session and also can discuss final project. Okay. So deep learning based object trackers started its rising around 2014. At first, it were mostly single object trackers. They were awkward and cumbersome. Let's recall the main difficulties of the object tracking in general. So first of all, it is a model development cost, from data collection to model feeding. So if it is so hard to pre-train your model for your tracking scenario, why not to tune the model while the runtime? And this idea was brought to the life by once popular MDNet tracker. It was trained to track each video domain separately. Each of the domain has its own head and a shared body. In runtime, it was necessary to feed a new head online, especially for your audio stream. Sorry, for your video stream. Let's take a closer look at this procedure. At the pre-training stage, we take our frames with known object positions, generate dozens of proposals, negative in blue and positive in red around the object. Positive, by the way, have high intersection over union with the object itself, and negative has low intersection over union, you see. And we challenge our separate heads to solve a binary classification problem, just to distinguish positive crops from negative ones. Looks like an object detection simulation, right? But there is no object detector here, though. The online stage is even more confusing. We also generate proposals, now much more negatives, and filter them using hard negatives mining, and tune only our fully connected layers. In the first frame, we do this straightforward because the precise location is known, the precise location of the object. From the second frame, we use certain rules and heuristics to update the network or not to update the network. Also, in the first step, we train an oscillatory rich regressor. It helps us to sample positives. Such twofold training procedure was quite difficult and slow, obviously. To be fair, the real-time version of the MDNet was suggested in 2018. But honestly, I'm not sure it was in demand. Meanwhile, an effective offline learning procedure was still highly desirable. One of the earliest and successful works was GoTurn, a very well-known tracker of the time. It is noteworthy that its idea is very simple in comparison to MDNet. The authors fit to the SAMS network and extended crop of the target object. I mean, the crop is larger than the bounding box itself. From the previous frame and from the current frame. The crop center is from the previous frame, obviously. And the network predicts the crop coordinates on the current frame. It is simple and efficient. GoTurn effectively trained on video, but extending the dataset with still images pushes the resulting quality higher. And the image datasets are really widespread. Another significant trend in the evolution of object trackers was perhaps the usage of recurrent neural networks. As an example, a roller tracker. The authors combined the features of the classification model, a simple classification model, the detector, and put everything to the LSTM. It worked, but it was heavy and slow. Here we already see the usage of step rate object detector. Another example of RNN-based tracker is reinsert. Such a blend of roller and GoTurn, you see it's already two streams with current frame and a future one, the same building blocks, and somewhere here is LSTM also. This already was a super real time, so it was successful, at least by some metrics. I mean, maybe not in real life scenario, but according to metrics. So SORT was released the same year as GoTurn and Rolla, becoming de facto the default algorithm in the MOT field, multiple object tracking. It was as simple as effective. What do we learn from this work? So first of all, the high quality detections are necessary for the high quality tracking. And this is true for any tracker. I mean, everything starts with a good detector. Strictly speaking, the detector is not a part of the sort at all. The sort is a Kalman plus Hungarian, right? So we have evolved from end-to-end training of the tracker to its case-dependent parameterization. And we already can train a good enough object detector. Well, does this mean that the high-quality detections are enough for the high-quality tracking? No. No, by definition, because detections are single-frame information, whereas our objects of interest live in time. Even with perfect detections, Kalman doing well only for monotonous and smooth object movement. But this is actually a small fraction of the real-life scenarios. However, a year later, the authors of DeepSort found out a killer feature for the person tracking, the appearance of a person, which turns to be even more informative than the movement itself. Positioning, however, also has its own use. Don't discount it. What are conclusions? High-quality detections have only become more important. They are needed for both re-identification and movement prediction. So, two wonderful works released the same year, breathing life into the field of object tracking. Of course, a lot of works have been proposed before it, but it seems that nothing could compete with deep sort plus heuristics in terms of generalization, ease of modification, configurability, right? Important prerequisites for both works were the appearance of so-called anchor-free object detectors. The authors of tracking object as points based its model on the CenterNet object detector and anchor-free object detector, expanding the concept of detection to a track. To this aim, the authors, firstly, add 3 additional channels of the previous frame, 3 additional channels of the previous frame to the input, and another one containing a heat map with objects from the previous frame, also from the previous frame. So 7 channel input. Such an extension of the input adds a temporal consistency in detection predictions. However, it is still not enough for tracking. The second modification that authors made is the prediction of 2 additional channels as the output, which contains the offset of each object between previous frame and the current one. After that, the simple gradient matching is enough for our single frame objects to become a real temporal tracks. Thus, the authors are moving from the tracking by detection paradigm to the joint tracking detection, making the detector the central and, in fact, the only component of the tracker, even without help of re-identification. The authors demonstrate the superiority of this approach over the Kalman, and similarly to GoTurn, it can be trained not only on videos, but also on images, on still images. Overall, it's a beautiful, well-written paper and with great ablation study, and really recommend for self-reading. Authors of the FAIR mode first showed us why anchor-based detectors are not suitable for the object detection and tracking. So, for example, multiple anchors corresponds to the single identity, making re-identification features ambiguous. And even one anchor can correspond to multiple identities, making re-identification features messy. And anchor-free detectors don't suffer from this, actually. Authors based its model on the same CenterNet detector, attaching area ID head in a parallel to the detection branch. How it looks like. So it's just an additional 128 element layer after the backbone, followed by a classification layer with the softmax activation. So authors solve a plain classification problem for identification, where the number of classes correspond to the number of unique identities in the data set. So having detections along with the identification features, authors apply a similar to deep sort strategy of matching and associations. Similar to GoTurn and center track, authors suggest to use still images for training, and actually only still images, because its model works single frame without while the temporal aggregation is done somewhere further.
I have a question. What is the difference between training on I mean, what do you mean? So we have training on still images and we have training on videos. What are these still images? Do you mean still images like frames of the video or something other than that?
Yeah, still frames. It's single frames from video or from everything else. Just a standalone image. Still frame is a standalone image. Because in video we have some consequence of images, right?
Yeah.
Where the object moves from frame to frame. On still images we have only single object position.
But how can tracking be trained without other frames? I don't really understand it, because we need to have the information about, well, how can we know, for example, offset if we don't know information from the previous frame?
So the idea of the frame mode is to train a joint detection and re-identification. And after generating detection and re-identification proposals, we put everything to the something like deep sort strategy. When you have Kalman filter, when you have assignment procedure, and some other like minor procedures.
Okay,
right?
I think I understand now.
Yeah, and center track, for example, trained already to track. So apart from the center track itself, was only a greedy matching algorithm based on the predicted offsets, while the fair mode is just a joint detection and the identification model.
Okay,
So yeah, thus we can conclude that the most accurate tracking algorithm is inseparable from the detections, right? And must be trained somehow together in accordance, in correspondence. So let's get back to the tracking problems. To one degree or another, we have tackled first two problems, right? The cost of the model development, the predictable movement, and we have a third one left. How can we unambiguously determine the quality metric of our tracking algorithm and make a fair comparison with the others? So let's figure it out. To begin with, we can define the simplest and most intuitive metrics. For example, let's perform matching of all predicted trajectories. Trajectories mean trajectory mean tracks, so it's the same. Let's perform matching of all tracks with the ground truth trajectories. If the ground truth trajectory covered by the predicted one at least on X% of frames, right? We consider them matched. Such we can calculate how many ground truth trajectories we have covered, or what percentage of trajectories. This is the mostly tracked metric. Number of fragments is the number of predicted trajectories that covered no more than X% of the corresponding trajectory frames. Usually thresholds for mostly tracked and fragments is the same number. So in mostly tracked we look for at least X%. In fragments, we are looking for no more than X%. Mostly lost is the number of ground truth trajectories covered with our predictions by no more than X% of frames, no more. Usually, this threshold is selected accordingly to mostly tracked. I mean, if in mostly tracked, we want to see the coverage at least 80%, then in mostly lost, no more 20%. However, this is not strict. And false trajectory is the predicted trajectory that have not been matched to any ground truth trajectory, just extra. In ID switches, we do not consider the predicted bounding boxes, but rather the resulting track IDs, track identities, and calculate the number of times when the identity changed along the ground truth track lifetime, right? So this group of metrics was developed in the early 2000s as a part of the classification of events, activities, and relationship workshops, or simply CLEAR, and finally published in 2008 in this work. These metrics are widely used to this day, being some standard. Here, everything is around detections, because detections uniquely defines our tracks, right? Frame by frame, we assign predicted detection to the ground truth based on the intersection of union. If the ground truth detection was not matched with any of our prediction, then this is obviously a false negative. The number of false negatives is in the entire video or set of videos is the first clear metric. Similarly, if one of our detections was not matched on a certain frame with any of ground truth detections, then it is a false positive. The number of false positives on the entire video or set of videos is the second clear metric. Each time the ground truth trajectory was interrupted due to the lack of associations, trajectory means track, on the certain frame, but later matched again, this is +1 to the fragmentation metric. So interrupted and later matched again. This is +1 to fragmentation. This is the total number of interruptions of the trajectory for the entire video or set of videos. And the already familiar ID switches. So we have introduced a little less than 10 different but kind of similar metrics. Someone would ask, how exactly can we compare algorithms between each other? How to interpret dozens of metrics at once? In fact, there are even more metrics. For example, there are also bounding box localization metrics. But we are interested more in some high-level metric that would aggregate simpler ones inside it. So one of these cumulative metrics is mod A. Note that it can be negative. If your algorithm generates a lot of extra objects, a lot of objects skips or often changes its IDs. Ground truth here is the total number of ground truth boxes, bounding boxes. This is the sum analog of the classification accuracy, actually, but in the tracking context. Of course, this metric is not ideal, but used for the comparison very often. We can also calculate mod P. Here, C is the number of matched detections on the frame T, right? D here is the intersection of a union between predicted and ground truth bounding boxes, which we sum up over all match detections. I mean index I. I is all detections. Someone would notice that this metric is more about the quality of detections than the quality of tracking, though. Nevertheless, this metric is widely used because, as we already know, there's no good tracking without good detections, right? So we have reviewed a set of atomic metrics of tracking and identification quality, a high-level metric of tracking and detection quality. Now we will consider high-level identification metrics. As you remember, depending on your algorithm, your identities can be either from tracking, from re-identification itself, or cumulative. So to calculate these metrics, a completely different procedure of predictions and ground truth matching is used, where we operate with the whole tracks and their IDEs instead of frame-wise detections matching. To the same, the biparate graph is constructing, and the problem solves globally. I mean, we perform matching over the whole video at once, not frame by frame. You can read more in the original paper. As a result of this procedure, we get a number of true positives, and false negative IDs. Having them, we can calculate the following metrics. In fact, these are precision, recall, and F1, which I hope familiar to everyone. But here or there are in the tracking context. Or more precisely, in the meaning of the accurate following object through the video, right? So all these metrics, which already reviewed, overemphasize the importance of either detection or association, higher the tracking accuracy, or simply hot A, covers detection, association, and localization quality at once, and can be decomposed into a set of submetrics which are able to evaluate each of these 5 basic error types separately, right? Hot A measures how well the trajectories or tracks of matching detections align and averages this over all matching detections, while also penalizing the detections that don't match. I mean ground truth detections that don't match. Here, TPA stands for the two positive associations. VNA stands for false negative associations, VPA for false positive associations, and A of C authors call association score. And alpha here, you see, is the localization similarity threshold. So it's some localization similarity score. Authors claim that the HOT-A scores much better aligns with the human perception of tracking quality in comparison to the previous metrics, including MOT-A, for example, or ID F1. I really recommend this paper for the self-reading because it's well written and puts everything in its place. So we have reviewed all the main checking metrics. A logical question arises: how do we calculate them in a correct way? I mean, how to fairly compare with someone else? Except the metric calculation procedure itself, we also need a standard procedure of ground truth and predictions matching, right? Because it's not always easy. Of course, there are ready-made tools for metrics calculation. If someone has already started the final project, already know about the MOT challenge. And this is an analog of the ImageNet large-scale visual recognition challenge, but for tracking. The challenge has its own toolkit for tracking results evaluation. Curiously, is that in 2021, the toolkit from Hot A authors replaced the original one, and the Hot A metric itself became general for the algorithms comparison. You have already seen this code if you have started the final project. Another good toolkit is PyMod metrics, by the way. You can use it. Looking back to our checking problems, specifically to fair metrics for the evaluation and comparison, in my opinion, exactly the Hot A made us closer in solving this problem. Okay. Well, in conclusion, let's look what the typical surveillance system consists of. I mean, from the architectural or some conceptual point of view. So this is the architecture of the typical surveillance solution. Here in bold, there are part of almost any surveillance system. And here in gray, more optional part. Here in red, we see a block of models that is not directly related to the analytics or computer vision. Tracking itself can be missing if you completely rely, for example, on re-identification. But at least you still have some tracks management here, something else. So let's take a closer look at this block of models in our pipeline. So to start track something, we have to detect something at first. Any surveillance pipeline begins with the detection of objects of interest for their further analysis and tracking. At the same level of the pipeline, additional attributes of the skin are collected or can be collected. For example, illumination, weather conditions. We can collect some calibration information about our system. For example, can monitor the camera tilt, perform leanness detection, etc. These models works perfectly in a batch mode, since they do not have temporal dependencies. In fact, this is the most independent and parallel place of the analytics. We can even process frames from different timestamps and even from different cameras here. The performance of these models is also stable and predictable since they work on the whole frames. Going further, this is the level of attributes generation for object detected on the frame. The most important attribute of an object in any modern surveillance system is its identity. Identification can be different and not necessarily for humans. The most common examples are identification of a person by body, by face, and also car plates recognition. However, there are much more attribution models. There are also face detectors, for example, if it's not performs on the whole frame, skeletons on a person, facial landmarks, gaze detection, and much more. This set of algorithms also works fine in batch mode due to the lack of temporal dependence. However, it's already more difficult to collect batches from different cameras. Firstly, because different cameras can assume the recognition of completely different attributes. So completely different models. And secondly, it is much more difficult to maintain the batch size since you don't know exactly how many objects will come from the previous step. For the same reason, these models are more difficult to load balancing and parallelization. Okay, the next level is the models that work with physical objects. These objects that live in time and have personal characteristics. Such objects can be humans, vehicles, animals, everything that or whom we want to check and analyze. Exactly at this level, the information for our business logic and decision-making system is generated. For example, open a door, raise a barrier, call emergency, and so on. To begin with, let's perform a fairly simple procedure. Using our identification features, identification signals from the previous stage, assign to each detection on the frame an identity from our identity database or create a new identity. It does not matter if it's a person, a car, or anything else. The result of this step is a complete identity field for each of our detections on the current frame. In the case of multimodal identification system, this is done for each modality separately. I mean, separate identity for the human face, separate identity for human body, etc. The next task is a little more complicated. We need to assign all the detections from the current frame to the already known objects, our tracks, and initiate new tracks if needed. As mentioned earlier, we can omit the checking component in the checker, relying entirely on identification subsystem if our model is so accurate. But modern trackers are usually multimodal and use the maximum information from the previous step for decision making. If you use a ready-based tracker like a deep sort, for example, it doesn't mean that you have to use the same model both for tracking itself and identification itself. On the contrary, it may be more reasonable to use very powerful but heavier, maybe more limited model for the identification itself and lighter, more generalized model for the tracking. Or you can perform identification solely by face and tracking by body, for example. This main thing, the main thing is to understand that these stages are not strictly dependent. I mean, the identification stage and the checking stage. So what do we have now? We associated each of our detections on the frame with the existing tracks and generated an identity candidate for each detection modality separately. But our objects of interest live actually in time, not on the single frame. This is where all the magic happens. We can just assign the identities predicted on the current frame for the whole track and, for example, immediately append the corresponding feature vectors to the identity database. Why? Because any model, any algorithm are not perfect. They make noise. Especially what about the tracking? Tracks can leave, appear again, and change their IDs. That's why we need some temporal aggregation. Only watching how the track identity changing over the time, we decide who is the track right now at the current frame. The same thing with modalities. Different identification modalities not always agreed. For example, facial re-identification models, as a rule, are more accurate than body models. So we need to somehow combine the decisions of individual models on the single frame and with the observation history and make a final decision about who we are currently observing on the frame. Sometimes even propagate this decision backwards in time to avoid future errors or to resolve some collision we made. This is a really important step. Unfortunately, there are traditionally a lot of heuristics and case-dependent solutions here. It is important to remember that no matter how accurate your models are on the validation data, RID models, for example, in reality, you will often have conflicts when several tracks receive the same identity on the current frame. And it is necessary to have some strategy to resolve these conflicts. In the simplest case, you can resend conflicting identities to the default ones. And finally, when temporal aggregation is done, when we're absolutely sure who is who in our frame, we can perform some post-processing, create new identities in the database, update the feature vectors of known identities, delete all tracks, and etc., etc. So it was the most algorithmically complex place of our system. And it is also the narrowest one. Processing here is often frame by frame, not in batch mode, due to the high temporal dependence of the algorithms. Batching and parallelization are difficult here, really, as well as the performance estimation, performance planning, since it also depends on the size of our database, the size of individual clusters, the number of conflicts we got, the length of tracks, and so on. Of course, the pipeline itself does not stop here. Further, you can aggregate all the information you've got, perform actions accordingly, generate reports, make visualization, dump results, update the database, storages, so on. But here the analytics stops and everything else is out of our scope. So here I probably stop my speech for today, and we have a time for the question and answering session, and we can also discuss final project implementation.
Well, I have only one question about the presentation. When we talked about single frame metrics, we had such things like false positives, false negatives, and well, everything like that. So, for example, false negatives, how do we calculate them? Do we use intersection over union, or is there another strategy on how we can do that?
Well, you're speaking about clear metrics, right?
Yes.
Okay, frame by frame, you compare your detections with the ground truth bounding boxes, with ground truth objects. And frame by frame, you decide how to match them based on some intersection of a union strategy.
So it introduces another parameter that we have to choose.
Of course, but as I said, these procedures are standardized. There is no need to invent a bicycle. You just follow the procedures everyone follows.
And I didn't really understand what is an identity switch. Could you
Yeah.
go to that slide that shows?
Okay, imagine you have some ground truth track.
Yes.
Right? From frame 0, it was alive from frame 0 to frame 10, for example. Its ground truth identity, for example, I don't know, number 15. And in some way, you match this track with frame by frame with your detections. And you also have and your detections uniquely define your tracks, your internal tracking IDs, because you are also working with tracks. And such you can conclude that this ground truth track is your, I don't know, track number 3, but sometimes it changed its identity. For example, most of the frames, it was a track number 3, your track number 3. But sometimes identity changed, and the number of when it happened, it is exactly a number of ID switches, right?
Okay, so in this example, it's not about the switches, it's about how many more tracks it has. So I mean, we have 1, 2, 3, 4, 5, 6 switches from one track to another, but we have 4 tracks here, and we subtract from 4 tracks 1, and we get this metric.
Yeah, we have 3 switches here. Switch to the purple track, to light purple track, and yellow track. Yeah.
Okay.
Yeah, because between 2 purples, it is not switch, of course. Yeah. We have another metric for this, like fragmentation.
Yeah. Well, yeah, I don't have any more questions about the presentation. But,
Okay, fine.
But I have a lot of questions regarding the final project.
Okay, go on.
Okay. Well, I will start with well, I want some advice on the overlay between the initial implementation and the best one. So if you in the presentation, how do I say it? If we draw boxes around each detection on the video 2 times, it would be too cluttered to understand anything. So, I mean, it wouldn't provide any useful information because we would have a lot of boxes that intersect with each other, and it would be really hard to understand what is going on there.
Okay, it's according to the overlays providing, right?
Well, we have. Let me open the page.
Yeah, number 6, provide overlays for the initial unmodified implementation and very best one.
Or do we have to do them separately?
Yeah, of course.
Oh, separate. Okay.
Yeah.
I thought
The
we
one
have.
result is for original deep sort, and another one for your modification, and you can stack them horizontally, for example, frame by frame, and will be really really cool demonstration.
Okay, thanks. Well, while that is out of the way, I have some real question about things. So somewhere below, yeah, uh, um, yeah, we have implementation rules number 5. It says your solution should have at least one real-time combination of models that works better than the original deep sort. But how can we compare original deep sort with our model, since deep sort doesn't have any detection model included? So the repository, the original repository of the deep sort, it uses detections provided by mod benchmarks, while in our project we have to add detection models so that it doesn't rely on these detections.
Okay, I don't see here anything about that you have to measure original deep sort. You're measuring only.
But how can we say that it works better?
We have a point in the rules for this. We are relying on the testing scenario. Point number 1, the target metric of the whole solution is hot A averaged between videos.
But hot A has to have detections, right?
Yeah, of course.
So we use detections provided by mod benchmarks to eliminate other like variables. So so we have to remove this detection step, and then we only compare deep sort with ReID, another not another ReID mod, but the feature generator that we had in deep sort with the feature generator that we have to use from another ReID model.
Yes, kind of it. So the meaning of the this point about FPS and performance is to, so we have a number of metrics like precision recall or F1 for the detector comparison, some metrics for identification comparison, and you just taking one of your solution, you will have few, no doubt, that like works better than the original deep sort with even with the ground truth bounding boxes, because original deep sort relies on the quite weak identification model, and when you replace the model, you will already get a better result. Even with YOLO, for example, I believe. But anyway, you can choose.
But
just
isn't YOLO detection model?
Sorry?
Isn't YOLO a detection model, not ReID? Or
So you just taking your best performing in quality, in terms of quality solution, and compare it. Oh no, it maybe not best, but any of your solution should work not slower than 5 FPS.
Okay.
Just a minute.
So I can disregard the another part of this sentence.
No, I
well,
explained that
we have
even you take
to evaluate them separately.
yeah, even if you compare the ground truth bounding boxes plus standard re-identification model of deep sort with YOLO detector and your re-identification model, even this combination should be better in quality, and you can compare how much.
Okay. Yeah.
Hot A will be higher.
And,
your hot A will be higher than for the original deep sort, even with ground truth bounding boxes.
So, and another thing, maybe I don't. We have an additional task, and I believe that the second point that we have on the website is just the explanation of the first, and the first is we have to add a standalone body re-ID, right?
Yeah.
But how is it different from the main task? I mean, isn't it the main task as well to create a or what does it even mean to add a standalone body re-ID?
So just recently, at the end of the webinar, I at the end of the lecture, I explained that it's not necessary to use the single re-identification model in your pipeline. You can use, for example, two models. What are the options? For example, you can use standalone identification. You can use more accurate body re-identification model by body, just for identification purpose, and lighter model inside the tracker. So tracker itself not generates identities. Tracker itself just assigns detections on the current frame to the already known tracks. It can do in many ways, including usage of re-identification models, but not necessarily. So identification and tracking separate parts of the pipeline. You can refer to the webinar lecture. Another option you can use identification by face, for example, because it's super accurate if face is visible, and you can traditionally use body identification model inside tracker, but this additional task number 7 is more about like using two body identification models.
Okay, so so in the main task we have to we have to follow these steps and do everything, and our model should work in real time. And the additional task is, in the main task, we have to have only one re-ID model, and in the additional task, we have to add another re-ID model so that it works better. So they should work in parallel, or I don't really understand.
The main task is to take a deep sort. You know how deep sort works. It uses detections. So deep sort is a tracker. It's not the identification model or detection model. It's just a tracker. It receives detections, and its aim to assign every new, like on the current frame detection, to the already known tracks, right?
Yeah.
Exactly, deep sort uses relies on the re-identification model for the same. Sort does not rely on the identification model, just Kalman and Hungarian. Deep sort relies also on identification model, but it's just tracking. Another step of the pipeline is the identification itself. Track ID, track ID is not the identity itself. It track because imagine you walking on video, right? It's video where you are walking. You are going out of screen, you are coming back, and you are still you are, but you already have few tracks generated. When you was here, when you was here, when you left, when you came back. So tracking identity, tracking ID is not a identification itself. It's so the
Oh, okay.
7.
Yeah, I understand. So so the when I was I started the project. So and for example, if we have for the same person, well, when I was testing it, for example, for the same person, I had I had tracks with numbers 1, 2, and 3, but it should only be 1, right? That's the
Yeah, I would say like identity, I don't know, Maxim would be would consist of track number 1, 5, 7, 10. It's how just it works
okay.
always.
So it also should work in real time.
Yeah, of course, because other way it does not make sense. They all working in real time.
So then it means that we only have to perform a re-identification well, step only when we get a new track, right? So if we don't have on the current frame a new track, we don't have to perform this step.
Okay, let me show again the today's slides, and I'll try to explain. So looking to this architecture, right?
Yeah.
Do you see my pointer?
Yes, yes.
Oh, cool. Okay, so imagine you received a frame. First, you so by the way, somewhere this I think this pipeline described step by step in the project description, but okay, we will
Yeah, I think
later.
I think it had something like that.
I mean, you receive a frame, you detect your object, so you have detections now. Now you generate. So if you do this additional task number 7, right? After having detections, you generate some identification uh, feature for them, like feature vector. I don't know. You can generate exactly identity right here from your database. Then you perform tracking. Inside tracking, you also can use some identification model, but these are different steps. After that, you have just after checking, you assigned your detection to already known check or created a new one. But then you have to say who this track is exactly from your database of known person.
Okay. So
And you have
it should work after everything.
yeah, you have some temporal observation, like on this frame I generated this identity, on this frame I generated this identity along the track. And you taking some observation window back in time, and finally decide who is who. What you need, what you really need for this, for completing this part is, let me show. Oh, I have description here. So yeah, the same pipeline written down here. You have to like create some kind of identity database, right? To search from someone. To assign some identity, you have to have some identity database. And you can register your new identity once you see it first time. Like you first time appeared at the video, you have body, for example, or you have face, and you immediately generate for it part a feature vector and store it in the database, some kind of database. And such you will like fulfill your identity database. And frame by frame, you just searching, just looking to this database and try to assign some identity to your new detection.
Yes. Yeah, I think I finally understand it now. But so and the next thing is so we have to look at identities for a time window. And why do we have to use a time window and not a single frame?
Yeah, I
So
discussed
that
it.
we can better decide the cluster in the database.
Yeah, some kind. I described it like particularly in the webinar lecture. You can rewatch. Yes, because all models are noisy, all predictions are noisy. If you rely on the single frame information, your real identity will change a lot of time through the time. You have to somehow you have to you want a consistency, some consistency in identity prediction, and that's why you have to look in some observation history to assign the identity based on the temporal window, not the single frame.
Okay. And if we so let's say that we have our time window of 3 frames, just for example. And well, first we can't perform this re-identification, but then after three frames, we perform this step. And on the 4th frame, do we have to go through frames 1 to 4, or we wait for another 3 frames and perform this step again?
Oh, you repeat this procedure every frame.
Okay.
You have some time window to look back and do it every frame.
Okay, yeah. And the last question, well, this one baffles me the most, and it's about a segmentation model. Why do we even have segmentation model here?
Why not?
I mean, I don't understand. Well, what should we what are we supposed to do with that? So
segmentation model almost not differ from the detection model, right? It's almost the same.
Yeah, but I mean, we have to.
I mean,
we just have to color people
model.
on the video, or what should we do with that?
Segmentation model works almost the same way as the detection model. You just find people on the frame and take their bounding boxes. That's all. Absolutely the same meaning of the than for the detection model. It's a person instance segmentation model. Human instance segmentation model.
Okay, so it should be on the same step as the detection model. So we have,
yeah, it's a replacement of detection model.
Oh, okay. So and so then I have a question regarding that. For detection, well, we generate bounding boxes, and then we use we generate some feature vector, and then we do something with the feature vector. But when we have a segmentation model, we are presented with a mask, right?
Right.
So,
but it's so straightforward to convert the mask to the bounding box, right?
Just so we convert mask to the bounding box and do the same procedure.
Yeah, you can experiment a little bit with the identification models, because identification model will work rather different when you crop your person from the detector prediction. I mean, the crop will consist of object itself and background, right?
Yeah.
And when you crop it from the segmentation model, you can apply mask, and your crop will consist of your object and, for example, 0 value pixels. And you can experiment how the identification model will work in such a scenario. It's just interesting to know.
But we don't have to. So it's only a part of the pipeline, and we don't have to show the masks or on the final.
No.
Okay. Yeah. Thanks. I think I asked all of the questions that I had regarding the project. And
cool. I hope this is the complete set of questions.
Yeah, I mean, I asked almost everything that I could think of. So, and what is the deadline for this project?
Oh, actually, you have to ask some management.
Okay.
I cannot answer you.
So you're not in charge of this.
Sorry, no.
Okay. Thanks. Thanks.
So I hope it was really useful. So what I tried to speak about today is some like general things that will, I hope will help you like in your real life, in your professional life. I will be glad to know about it. So good luck with final project with the REST course, and bye.
Thanks for the webinar. Bye.